Welcome back, everybody. We are looking at example 2 on page 30 of the workbook. This is a continuation of the discussion that we were talking about on the previous page. Let's read this together. So as in example 1, let v1 through v6 be the vectors forming the columns of the matrix A that's given to the right over here. If you look at those columns, v1 through v6, you'll notice they're the same vectors that we looked at in example 1. Okay, and as an example one, we're going to talk about the same subspace, okay, W being the span of those 6 vectors. Okay, now what we're being asked to do in example 2 is related to what we did before, so let's remind ourselves of the result of example 1. What we did in example 1 was we came up with a basis for this vector space, a set that's both linearly independent and that spans W, and it looked like v1, v2, and v5. Okay, so let's just label that basis from example 1. So what we're going to discover in this example is that bases are not unique. Okay, for a vector space, there are all kinds of different bases that you could have, but they all have a very important property in common. That's what we're going to kind of discover here. All right, so with that in mind, let's read part A. See what they're asking us here. So for each of the following, you're given a linearly independent subset L of W, the subspace that we're talking about, and a matrix with its echelon form. Use the information to write down a basis for W that contains L. Okay, so for example, in part 1 here, they're starting us off with a set that contains one vector in it. Okay, L equals V3. Now, if you look at the matrix over here to the right, notice that the columns of that matrix are exactly the same as the columns of the matrix up here, just that the order has been changed a little bit. Okay, so for example, V3 appears as the first column in that matrix, and then the other vectors follow, V1, V2, V4, V5, and V6. Okay, so it's the same 6 columns as what we have up here. So if we were to talk about the span of the 6 columns in the vectors in the matrix down here, we're going to get the same subspace W that we've been talking about. Okay, so we can follow the same process that we did in example 1, do row operations on this matrix, and we come up with the matrix over here to the right. And again, it's all about where those pivot positions land. Okay, so if we circle the first non-zero entry in each row, those are the positions that we get. And we know from the general principle on the previous page that we can get a basis for our vector space by just taking the vectors that correspond to those pivot positions. Okay, so what would the vectors be in this case? Well, they would be the vector in the first column, that's V3, then in the second column, and then finally in the 5th column. So it looks like it's V3, V1, and V5 this time. So what we have just discovered then is a second basis, okay, for this vector space W, but the basis contains V3. We kind of made our algorithm work for us so that we choose V3 by putting V3 to be the first vector in our or the first column in our matrix. That was the key to ensuring that our basis contains V3. Okay, and the rest of these are kind of similar. Okay, so 2 starts us off with a set that contains the vectors V1 and V4. We would like to come up with another basis for W that contains those 2 vectors. So what we do is make sure that when we write down our matrix, V1 and V4, okay, are the first 2 columns. Notice that, and I'm just going to remind you, I actually probably should have done this earlier, but the matrix that they gave us at the beginning, that just contains the vectors in the order that we started with. Okay, so just think about that as we go through it. And so this matrix that we're looking at down here has V1 and V4 as its first 2 columns, and then V2, V3, V5, and V6. Okay, so same 6 vectors, we've just changed the order again. Okay, and if you do row operation on this, row operations, and spot your pivot positions, there they are. And so this time, our general algorithm here picks out these three vectors. And so we know then that those three vectors would also be a basis for W. So V1, V4, and V5. And by making V1 and V4 the first two vectors or the first two columns in our matrix, that guaranteed that they're going to be part of our basis. Okay, one more example. Okay, this is just to illustrate the versatility of this method that we have. Suppose that we wanted to choose a basis for W that contains the vector 1, 2, negative 114. You might look at that and ask, where in the world does that come from? That's actually in our vector space because it happens to be the sum of the vectors v4 and v5. That's where that came from. Okay, so if you look at the matrix down here, that first column is v4 plus v5, and then the other columns are just the 6 vectors that we started with. Okay, and so if we do our usual row operations on this and pick out our pivot positions, this time we get pivots in the first 3 columns, which means that we're going to pick this vector, that's our first column, and then v1 and v2. Okay, so we get a basis then that looks like this. Okay, the first vector is v4 plus v5, and then v1 and v2. Okay, so we're seeing then there are all kinds of different bases, okay, for this vector space W that we're talking about, and we could then ask, is there anything that all the bases have in common? That's what this question B is about here. So what do you notice about the number of vectors in each basis from part A? Notice that in every single one of them, we got exactly 3 vectors. And it turns out that that's no accident. Okay, that's a very special property that a basis of a vector space has to have. You take a vector space, there are going to be a lot of different bases, but they always have to have the same number of vectors. Okay, we'll continue with that thought in the next video.